Hello everyone, and thanks for coming to my virtual presentation. My name is Pouya, and I'll be presenting our paper called SAT-based approach for learning optimal decision trees with non-binary features. Before we head into the details, just to give you an overview of what we'll be discussing today. We'll be talking about decision trees. They are popular classification models, and they have different benefits, including interpretability and accuracy. They're constructed using different methods, including greedy heuristics and exact methods. The recent advances in using exact methods for constructing decision trees have been very positive, but there's one shortcoming that they only focus on binary features. We aim to solve that problem, and we present an alternative approach to encode decision tree construction that directly handles non-binary features as well. And we aim to improve the performance on that regard. And we'll be talking a bit about the background. I'm sure a lot of you are already familiar with the background, but just to give you a quick reminder. We're dealing with the classification problem. It's a very popular application of machine learning. It takes a labeled set of data and it tries to model a function or a model that can predict the label of future unseen data points. Decision trees are a very popular form of model that we're trying to learn in classification. And their main benefit is that they're interpretable, meaning that they're fairly easy to look at in layman terms. They're human readable. A human understands what's happening in a decision tree. And because of their simple structure, you can use logic and different methods to precisely reason about their properties. And this makes them prime candidates for safety critical applications. If you want to solve a classification problem that involves certain situations that might be better for the user to understand what's going on or to prove certain properties, then you want to use these kind of solutions. This is an example of a decision tree, just to give you an intuition of what it's going to look like. It's basically a sequence of decisions. It starts from the top, and when you enter a new data point, different questions is asked at each branching node, and based on the answer to those, you go either to left or right until you end up in a leaf. So in each branching node, you choose a feature to ask the question about, and you have a threshold. If the value of that data point for that feature is less than or equal to the threshold, it goes to the left child, and otherwise it goes to the right child. And you keep doing the same procedure again and again until you reach a leaf. And when you reach a leaf, the label of that leaf is the label of the data point that you're asking the question about. And here we have an example of a company that tries to decide whether they want to hire a person or not, based on their age, their GPA, and their amount of experience. And these are the mathematical details of what I just described. So a tree it has a structure, it has a way of selecting features for each node, and it has a way of selecting thresholds and labeling its leaves. And then there's a recursive function that you can see on the right that recursively asks the question of where the data point should be directed until it reaches a leaf, and it gets the label. Now, we know what decision trees are. How are we planning to find them? And it turns out there are two primary ways to construct decision trees. The first one, which is a bit older and more well-studied, is local search and heuristics. So you start from a solution and you try to improve it step by step. Let's say you start from a single node and you ask the question, what split from this single node makes the most sense? And when you add that, you have two new children, and you can repeat the process for that children as well. The second approach, which recently found a lot of success, is combinatorial optimization. Is that basically you encode the problem of finding a decision tree into a combinatorial optimization problem that's already well known and it's easier to solve. And you solve that instead, and then you extract the solution. The benefits of the second approach is that it can guarantee optimality, because the problem that you're solving might be able to guarantee you optimality. And it provides you with a lot of flexibility, whether you want to add additional constraints, or you want to encode the objective in a different way, or you want to impose a certain property, you can do that as well. The optimization problem that we chose for this purpose are SAT and MaxSat. SAT is inherently not an optimization problem, but we'll see how we can use it to solve an optimization problem in future slides. A lot of you already know what SAT is. You have a set of binary variables and you have clauses, and you need to satisfy all those clauses by finding an assignment. MaxSat is just the optimization version of SAT. Instead of satisfying all the clauses, you have two sets, hard clauses and soft clauses. You need to satisfy all hard clauses, but for soft clauses, you just need to maximize the number of satisfied clauses as much as possible. Now, that concludes our background section, and we'll be going into details of the encoding. So we want to encode the problem of finding a decision tree into SAT and MaxSat. There are certain aspects of that that's fairly straightforward for a person that's experienced with working with those kind of combinatorial optimizations. For example, feature selection is a simple set of binary variables. Whether feature J, for example, belongs to node T. That can be a binary variable, and it's fairly easy to encode that. The same goes with leaf labeling and presence at leaves. The challenging part is the split that happens at each branching node and the threshold that we want to encode, because threshold is a very numerical entity and we're using binary variables, so that might be a challenge. There are multiple approaches for that, and the first one, which the baselines that we compare our results to use, is that they simply do not encode threshold. And they only encode features, they only support features that do not meet thresholds at all. And those are the binary features. For binary features, if the value is 0, the point goes to left. If it's right, it goes to right. There's no need for a threshold. And if you have numerical and categorical features in your data set, you can simply transform them to binary ones. As an example of that is provided on the right. But the problem is that if you do this transformation and you have a lot of different numerical or categorical values for each of your features, then you might end up with a huge number of new features as a result of that transformation. And that can be a huge overhead for the performance. And we're trying to fix that. So the second approach, which is the new idea, is that we want to encode direction, and we want to encode the thresholds of the splits directly. We don't want to shy away from doing that. And the idea for doing that is that for each data point and each branching node, we encode the direction in which data point is directed independently. So for example, if you look at the figure on the right, for each node, we know the direction for each of the data points. And in the next figure, for each data point, we know what happens to that data point in each branching node. First thing to note for this method is that we want to make sure that the order of values is respected in these directions that are encoded. So if a value 3, for example, is directed towards right, then the value 5 cannot be directed towards left, because 5 is larger than 3 and it's located on the right side. So we add a set of clauses that enforces that. And by doing so, we make sure that our splits are valid. One other thing to note for this kind of encoding is that, in a sense, we are encoding hypothetical splits, because again, if you look at the figure on the right, on the bottom, you see that the point never reaches the left children. But even though that's the case, we still encode the direction for that data point and for that branching node. And we do that because we want to have a chain of directions, and we want to use that chain of directions to validate the order constraints that we have for our values. And that was the idea. So using that idea, we'll be moving into the details of our encoding. We have 4 sets of variables. The first one is for feature selection, which is called A. S is for encoding the directions at each branching node and each data point. Z presents the presence of points at leaves of our tree, and G represents what the label of each leaf is going to be. And the parameters are the usual suspects. You have a set of features, integer labels, training examples, and labeling. There's one additional parameter compared to what you normally see in classification, and that is the tree structure. We want to know what our tree looks like, and in the next slides, we'll see how we can settle on a tree structure. But for now, we assume that we have it. And clauses are fairly straightforward as well. So for example, the first set makes sure that only one feature is chosen at each branching node. The second set imposes the order of directions that we discussed. And the third one makes sure that our splits are non-trivial. So we don't want to direct all the points to left or all of them to right. We want to have a split that is meaningful. The fourth one makes sure that whenever we say a data point reaches a leaf, that presence matches all the split decisions that are made along the way to that leaf. So this is a bit more complicated, but still fairly easy to follow. And the last one just makes sure that a leaf in the tree doesn't have two labels, because that's cheating. Because if you do that, we're able to correctly classify two conflicting data points. Okay, and now we know how to encode a decision tree, but we assume that we have the tree structure. So we want to know what that tree structure is, how we can settle on one for our input, and what kind of objectives are we optimizing. So we optimize two objectives that are well studied. The first one tries to minimize the depth, optimize the depth, but it also wants to correctly classify all of the training points. So we want a tree that is as shallow as possible, but it correctly classifies all of our data. And in order to do so, we just increase the depth one by one and use the SAT instances to see where a solution is found. For the second objective, we want to settle on a depth. We don't want to change the depth, but we want to find the best tree possible for that depth. So we're maximizing the number of correct classifications instead. And because the problem that we are solving is a maximization problem, and we need to use max_sat instead of sat for the second objective. Just before we head into the experimental section, I just wanted to mention one last thing. Our approach supports categorical features as well. Due to space and time constraints, I wasn't able to include the technical and the experimental aspects of that in the slides. But I just want to briefly mention that the same idea can be used for categorical splits as well. The only difference is that here we don't need to validate order, because there's no order in categorical values, and each one of them can be directed to left or right separately. And exactly because of that, this enables power set branching as opposed to one-hot branching. And this means that we can have a subset of values directed left and a subset of values directed right. And this kind of branching is obviously more expressive than one-hot branching. So it might potentially lead to more shallow solutions for mean depth objective, or more accurate solutions for max accuracy objective. Okay, and that concludes our encoding, and let's head into the experimental section. The setup is that we want to have two different implementations for the two objectives. The first one is done in C++ and Minisat solver is used, and the second one is done in Java, and the Loandra max_sat solver is used. We chose 3 different baselines that are all very new, and they're all state-of-the-art algorithms for their respective objectives. The goal of the experiments is not the quality of the solutions, because the 2 objectives that we are optimizing have already been well studied, and their benefits and their applications are well known. Instead, we want to do exactly what the baselines are doing, but we want to do it in a shorter amount of time. So we want to improve performance. We want to find the solutions faster, and even if we time out and we're not able to find the solution, we're not able to find the optimal solution, we still want to find a solution that's really good and it's near optimal in our timeout scenarios. Before we head into the results, I wanted to mention what kind of data sets we're using. So data sets are divided into 3 groups, mostly numerical, mostly categorical, mostly binary. We included binary features as data sets with binary features as well, because we wanted to have a complete picture of how our algorithm performs. But generally, we expected the baselines to perform better on binary features, since those are not our primary goals. One additional thing to note here is that by mostly, we mean that, for example, a mostly binary data set is not necessarily an all binary data set. It might have numerical features, but that numerical features don't have a lot of different values. So in nature, they're more close to a binary data set or a binary feature instead of a numerical feature. And the same goes with mostly numerical. And if you look at the data, we try to cover a wide array of data sets. For example, we have data sets that are more than 1,000 points in size, and we have of different types, different number of classes and different applications. The results, let's compare the results with our baselines. First, so for example, for the first objective, the mean depth objective, the results are as we expected. Our approach is significantly faster than the baseline on non-binary data sets. And on binary data sets, the baselines perform better. We see that in the improvements that our algorithm achieved, we have cases in which the baseline gets a timeout, but we solve the problem in a fairly fast way. And even if the baseline does not get a timeout, we still solving the problem in a shorter amount of time. And the same goes with the max accuracy results. On non-binary data sets, there are significant improvement for our algorithm. But for binary, the baseline performs better. But one additional thing to note here, and I think it's really interesting, is that even though for binary data sets, our approach is way slower, it still manages to find near optimal solutions for 5 out of the 6 cases. So even though it gets a timeout, it still gets a really good solution. In fact, the optimal solution in 5 out of the 6 cases. And that concludes our experimental section as well. Just to give you a summary of what we discussed today, we presented a MaxSat-based encoding for constructing optimal decision trees that works particularly well for non-binary features, namely numerical and categorical. It can be used to solve 2 different well-studied objectives, namely mean depth and max accuracy. And the categorical part supports power set splitting, which might result in a more compact or more accurate solution. And the experimental section shows that our algorithm, as we expected, outperforms the state-of-the-art for the non-binary data sets. And that concludes my presentation. Thank you so much for your time. And if you have any questions, I'll be happy to take them.